Hi, welcome to the next in our series of Practical Electromagnetics for Engineers. We've been doing a lot of theory and a lot of math so far, and I think it's time to start to roll this theory and math back into something a little bit more practical. So today we're going to be talking about the relationship between charge and voltage, and we call that capacitance. If you're one of my students, you can follow along in section 4.9 of your textbook. So far we've defined three different ways we talk about electricity: the charge, the vector field of electric field or flux, and the scalar field of potential or voltage. Now the charge, you remember, is a fundamental property of matter, kind of like mass. Things have mass or they don't have mass, and just like things that have mass exert gravitational fields that pull on other masses, charges only affect things that have charge. So charge doesn't affect stuff that isn't charged. The electric field and the flux, D, are vector fields that are created by these charges. And electric fields are force fields that push on charges, and we think about the flux as the amount of force raised per unit area. The voltage, which is a scalar field, is the potential energy field created by charges. And the potential energy of a charge is the voltage at that spatial point of the scalar field. Is the value of the voltage multiplied by the amount of charge. There are relationships between charge, field and flux, and voltage, and these relationships are mathematical, and we've derived a lot of them and expressed a lot of them in the last video series. And this sort of leads us into a conundrum, is that if we have to work with electrical engineering things by doing a whole bunch of integrals or complicated three-dimensional derivatives, we're never going to be able to get anywhere and design anything. So we need to sort of simplify this and look at some ways to sort of aggregate these relationships in ways that are simpler to understand, that really are heuristics or sort of rules of thumb for working with electricity. So in order to do this, let's talk about the relationship between voltage and charge, and consider what you see here. Two metal cylinders, one with a charge plus Q and one with a charge minus Q. And we haven't talked about the relationship of electric fields and electricity in metals anymore, but suffice it to say that if you have charge in a metal, that charge is free to move around in any way you want. So let's look at an end-on view of those two cylinders here, and the little plus charges essentially are all going to aggregate on the side closest to the minus charge, for the simple reason that we know that plus charges and minus charges attract one another, and these charges are free to move. Similarly, the minus charges are going to sort of be as close as they can possibly get to the plus charge, but not so close the force from minus charges pushing against one another overcomes them. So what happens here? Well, it's pretty obvious. If we have a bunch of plus charges and a bunch of minus charges, we know we're going to get an electric field that starts on the plus charge and it ends on the minus charge. We can also think of these as flux rays if we want to. And so we're probably going to get basically an electric field that looks something like this. And you can find electric fields that look like this in practically a textbook, on lots and lots of videos on the web like this one. So what does this have to do with our relationship of voltage and charge? Well, we know charges create electric fields or flux vectors, and we also know that if we're given the electric field and the permittivity, we can calculate both the voltage difference between these two metal cylinders, let's call that delta V here, and as well as the charge on the cylinders, Q. We know that the voltage difference is simply given by the negative of the line integral of the electric field along any path. So if I simply go step by step along any one of these electric field lines, it doesn't matter which one, integrating the direction of the line with the direction I'm marching, dl, I'm going to get the voltage between these two cylinders. Also, I know from Gauss's law that the charge enclosed within any closed surface, so this is a surface integral here, and this little round arrow means it's a closed surface. If I integrate over a closed surface, the flux, d, or epsilon e, dot producted with the little surface vector, what I'm going to get is that I'm going to get the total amount of charge enclosed. So if I draw sort of a surface around this in 2 dimensions and in 3 dimensions, it might just be sort of a cylindrical surface that looks like this. And I integrate the electric field times epsilon, or the flux vectors that come out of that, it gives me the charge enclosed. So once we have the electric field, at least theoretically, we can calculate the potential difference in the charge, and we can relate those things. No surprises here. the question we want to ask is, are there some simpler relationships between the voltage and the charge? Because if I have to calculate a line integral in three-dimensional space and a closed surface integral in three-dimensional space every time I need to work with something, it gets a little tedious. So let's do some thinking about how the voltage difference and the charge are going to change as I change some things in this diagram. So let's start by looking at what happens if I double the charge, for example. So essentially what I've got is I've got a charge 2q on this cylinder and minus 2q on that cylinder. Well, it's pretty straightforward what's going to happen here. If we think about our vector field of the electric field, if we had charges that looked like, if we had a field that looked like this for the charge plus 1q and minus 1q, if we double q, we're going to get twice the electric field. So essentially what we're going to have is we're going to have longer arrows, a stronger field. And we know that's true because the electric field, if we plot this out and do the equation, the magnitude of the electric field vector is simply proportional to the amount of charge. So essentially what happens, if everything remains the same here, I do exactly the same integrals and I just double the amount of charge, then I'm going to double E, and the ratio between voltage and charge remains the same. So if I write this essentially as a ratio between the charge to the voltage, that ratio stays the same if I double the charge or half the charge or even get 10 times as much charge. Let's take a look at another case. In this case we keep the charge as basically plus Q and minus Q, but what we've done is we've increased the separation between our two wires here. What happens in this case? Well, you're still going to get the same types of electric field lines that go between them. So let's look at the charge and the voltage. Well, the charge is that surface integral, and if I basically do my surface integral that looks something like this, right, and I put a can around this and I integrate over that can, essentially what I'm going to see is that the charge remains the same. This integral here has absolutely nothing to do with the distance between them, so that simply remains Q. The voltage difference between them has everything to do with the distance, because essentially I do this line integral along this little path from one to the other. So if I double the distance, then I would expect my voltage, in fact, to double. But we also have to remember another thing. We have to remember that the electric field itself is related to the inverse square of the distance, because we've got a cube down in the denominator, we've got distance to the first power up in the numerator, and so the electric field drops off as 1 over d squared, while voltage just increases as d. So overall, what I would expect is the charge to remain the same, because I'm doing the integral right around the charge, but as I go along this line, any line connecting two of my charged metal cylinders, the overall voltage is going to drop because of this inverse square and linear dependence multiplied together. So what does this mean? It means that the ratio between charge and voltage, charge to voltage ratio, is independent of either the charge or the voltage, but it depends a lot on the geometry of the thing I'm calculating. And we call this ratio of charge to voltage the capacitance. We use C for capacitance, and we measure it in farads. And farads, the capacitance in farads, is just the charge in coulombs divided by the voltage in volts, and we can calculate the capacitance fairly easily simply by the Gauss law integral over a closed surface to determine the charge, divided by the line integral in space to determine the potential. Furthermore, because the capacitance doesn't depend on Q and it doesn't depend on V, it only depends on the geometry. For any type of geometry, we should be able to determine a capacitance that's completely independent of how we use this thing. So if we determine a capacitance of a structure in a circuit, it doesn't matter what voltage or current runs through this, the capacitance stays the same. It's just a function of geometry. And now you start to see some of the use of this electromagnetics is you use this to calculate things that matter in building circuits, like capacitance. And you have to understand what we mean by geometry here. Geometry is not just the spatial arrangement of these wires. For example, I would get a different capacitance if I use square wires rather than round wires. But because we're talking about the flux vector to calculate Q, in other words, we use epsilon E, it also matters the materials that are around and surround these wires. So for example, if I had a block of material of permittivity epsilon that was between the wires or anywhere that intersected one of the electric field vectors created by those wires, it would change the capacitance. And fortunately, we have a really nice expression that captures all of this that doesn't involve integrals. We say the charge induced on a structure is equal to the capacitance times the voltage. So let's investigate this seemingly simple law and look at a couple of cases. The first case we're going to look at is taking this law and dividing it by some integral or sort of interval of time, delta t. So we simply take both sides of this equation and divide by delta t, which is shown right here. We know that a change in charge over a change in time is called a current, because currents are just flowing charges. So we can rewrite this as I. And we also know that a change in voltage over time, if delta is small, we can write as a derivative, and voila. From this, we've all of a sudden derived one of our basic circuits law, which is the current is equal to the capacitance times the time rate of change of voltage. We'll come back and use this in just a little bit. Now, it turns out that we can solve this equation, this surface integral divided by the line integral, in cases that have simple geometries, just like we did with transmission lines, and find analytic solutions we can use in all kinds of cases. The most common one is parallel plates. So to understand parallel plates, let's take a sheet of charge, an infinite sheet of charge, and the charge on this sheet is plus Q. We know it's going to create an electric field, and this electric field is just going to point away from the charges, because all the components of the charge that go this way and this way are going to be canceled out by the components above and below it. So we're going to get an electric field vector map that looks something like this. Now let's do the experiment where we take a similar sheet of negative charge, minus Q. We know that in this case the electric field vectors, which I've shown as blue arrows to distinguish them, are pointing toward the sheet of charge. And look what happens. Because we have an infinite sheet, the electric field vectors cancel out on either side of the two sheets of charge because they're pointing in opposite directions. But they add together between the two sheets of charge. So if we have two sheets of charge of opposite charge, plus Q and minus Q, we're going to get no electric field out here and a very strong electric field between the two plates. We call that a capacitor. So essentially what we do is we take two metal plates and we put a charge plus Q on one metal plate and a charge minus Q on another metal plate. This is going to induce an electric field that looks like that points from the positive charged plate to the negatively charged plate. And essentially what we do here is we're going to ignore what we call fringing fields, which are the fields at the edges of this thing that essentially go out in free space and do some bending. And we're saying, gee, the plates are so big that the edge effects are pretty minor, and that's a pretty good assumption. And if we do this, and you can find the solution in practically any book on electromagnetics, you come up with this expression right here, that the capacitance of two plates is epsilon A over D, where epsilon is the permittivity of the material that's between the plates, A is the area of the plates. So if we double the area, we double the capacitance. If we increase the side of one of these plates by a factor of 2, it goes as the square because the area is the side square. And D is the distance between the plates, D. So essentially if we make the plates further apart, twice as far apart, the capacitance drops by a factor of 2, or essentially the ratio of the charge to the voltage drops by a factor of 2, which is what we found earlier when we thought about those two metal cylinders we pulled apart. It also means if you want a large capacitor, you choose a high epsilon material between the plates, have large area, and put the plates really close together. There are a couple other simple geometries we can get analytic solutions for as well, which include coaxial cylinders such as B and C cable, and also pairs of cylindrical wires, the example we did earlier. For coaxial cylinders, we're going to assume the inner cylinder has a radius of A, the outer cylinder has a radius of B. We've got some kind of material epsilon inside that cylinder, and then the overall capacitance is given by the equation below the cylinder, and we basically calculate that as a function of length. If we leave out L, we get the capacitance per meter, per unit length, and this is exactly what we used when we determined the impedance of transmission lines in the first set of videos. The expression for the capacitance of two wires sitting in space is more complicated. Here the diameter of the wire is 2a, and d is the distance between the wires, and this happens also to have epsilon, the permittivity of the material that the wires are embedded in. We have the length of the wires there, and we have a hyperbolic inverse cosine term there, which you have to either calculate or look up. But again, you have a solution, and so you know that any two wires have capacitance between them. So we're going to look at two cases on why we need capacitance, why capacitance is important. And the first case is if we want to store a lot of charge. We want to use the capacitor as an electricity storage device, because it turns out that batteries work pretty well for this, but batteries are based on chemical processes, so if you want to withdraw a lot of charge, a really high current, really quickly, batteries get hot and blow up and spread nasty chemicals or acid everywhere, which is not a good scenario. So if we really need to have things that use a lot of current very quickly, capacitors are the component of choice. Parallel plate capacitors are what we use for this. We know the capacitance is epsilon, the permittivity of the material between the plates, times the area divided by the distance between the plates. So you really have to have really big plates with a big A, a high epsilon material, and as small a d as you can practically engineer to get high capacitance if you want to store a lot of charge. The way this is typically done is you get like a very thin sheet of plastic and you put layers of metal on either side. So you'd have a thin sheet of plastic in the middle with a high epsilon material, and you'd cover one side with metal, another side with metal, and the red sheet is essentially the positively charged side and the blue sheet is the negatively charged side. But of course you never see these giant plate capacitors sitting around anywhere unless you go into sort of an ancient laboratory. So what you really do to make high capacity capacitors is once you have the thin sheet of plastic with metal on both sides, is you roll it up into kind of a cylinder, kind of the way you'd roll up a jelly roll, and this gives you a very large area in a very, very small volume. Let's take a look at another case of where you want to have very small capacitance, and we call this parasitic capacitance. We know if we have two wires, they're going to have some capacitance between them, and we have an expression for that, complicated as it may be. We also know that we have some relationships between charge and voltage that are given by the capacitance, and we can express that as the current being equal to the capacitance times the rate of change of voltage. So let's say that these two wires we have signals on in some kind of circuit, and we are giving essentially along one of these wires some kind of pulse wave. We have basically data pulses, ones and zeros if you will. So here's a 1, here's a 0, at a high bit rate that we're passing through this wire, like internet cable for example. So the voltage is changing as a function of time. What does this mean? It means that when you have a changing voltage and you have a non-zero capacitance, you will induce a current. So since these two wires are connected by electric flux fields, because they have capacitance, what you get is you get a current induced on wire number 2 when you have a signal on wire number 1. And that current might look something like this, because you notice here the rate of change of voltage is large and positive. When you have a falling edge, you have a negative change of voltage. So you might get a positive going current pulse, a negative going current pulse on the falling edge, and so on and so forth. What have you done? You've coupled the signal from wire 1 into a signal on wire 2. This can create all kinds of havoc when you're sending high data rates on closely spaced wires on something like a printed circuit board or an Ethernet cable or something like that. And you notice the faster the data rate, the smaller delta T in your geometry. So at higher frequency, this parasitic capacitance becomes a bigger problem. So what are you going to do about this situation as an engineer? Because any two conductors are going to have some capacitance between them. Well, obviously, one thing you can do is you can increase the value of D or decrease the value of epsilon. But you don't always have the ability to have very tiny epsilons or put wires really, really far apart, especially on a high-density circuit board. So let's look at another technique. We know from our theoretical understanding we've developed that this capacitance comes about because electric fields couple these two wires together. If we could reduce this electric field coupling, we would reduce the capacitance, and by reducing the capacitance, making C smaller, this fact that we induce the current from one wire to the other becomes less of a problem. And here's how you do that in many cases. Essentially, you take another sheet of metal and you tie that sheet of metal to ground and you run your wires close to it. So sure, you do have some coupling of your electric field from one wire to another here, but you've got a lot more coupling of those charges down to ground. So rather than connecting the two wires together, we couple the electric field down into the ground plane, and by doing this we reduce the number of flux vectors that cut across this. By reducing this, we reduce our capacitance. So hopefully this has shown you some examples of capacitance and how we design things to either have big capacitance if we want to store energy, or minimize or have small capacitance between conductors if we're worried about getting crosstalk between wires or coupling one signal onto